there was only one lesson though, unfortunately, right? So last lesson we went through standing waves, right? We talked about how to create standing waves. Yeah, so now we're gonna, like, we talked about it. We talked about quite extensively how to get standing waves. And I mentioned to you there's like a difference between, let me see whether there's the field version. Yeah, right. There's a difference between the string wave, right? The slight difference between the string wave and the sound wave. Okay, because the string wave is both ends fixed, the sound wave is both ends open. So when you create a standing wave, the two ends of a string wave is a note, right? If both ends are closed or both ends are fixed, then both ends are notes. If it's a sound wave and if both ends are open, then both ends are empty notes, right? So that's one of the subtle differences. But essentially, the math behind it, the mathematics, is it the same? It's the same math, right? The math is the same. Oh, sorry. Do you have the notes? You have the notes, right? Okay, okay. No, because if you don't have, you can pick up a copy there. I already have some. Go back, go back. Oh, okay, nice. Okay, so the subtle differences will be like, oh, two ends closed, both ends are notes, two ends open, both ends are empty notes. The general formula is the same, right? The general formula is the same, right? Because as you go from first to second to third harmonic, sorry, choke. As you go from the first to second to third harmonic, you basically increase the shape by half a wavelength. But don't forget, the speed is always the same. You change the frequency, you're changing the wavelength, right? These are different wavelengths, okay? But the kind of like the pattern of the shape, right? You increase every half a wavelength with every harmonic, right? We call them harmonic. Now, some of you in school, you may have heard your teacher use the word fundamental frequency. That's still okay. Fundamental frequency is for the first harmonic. But if he says something else, right, just ignore what he said. So the standard way of questions being asked in IB is that they'll ask you for the first harmonic, second harmonic, third harmonic. They will never ask you, right, fundamental, right, and then what, first overtone or second overtone. Do you have the notes? Yeah. Oh, okay. You have the notes also. Okay. Yeah. I'm just trying to get rid of this. You want to sit over there? Yeah, go over there. Sit. Don't hit my camera. That's it. Well, that's a nice labu. Yes, the nice version. Yeah. Oh, nice. Hey, look, don't bully him lah. Okay. He is someone that give you even less space, right? Okay, so just take note of this, right? But there's one very big difference between a string wave and a sound wave. What's the very big difference that you have to be very aware of? I shout. What's the very big difference between the string standing wave and the sound standing wave? What's the very, very big difference? I mean, this is the same thing as what he's saying. The what? Say what? No, no, no. That's a subtle difference. I mean, both ends fixed means both ends are note. Both ends open means both ends are empty notes. What's a kind of like? I mean, I sort of like ended off with it in the last lesson. It's something to do with this. One's longitudinal, one's transverse. That's the major difference, right? It's about the wait, whose phone is on? Hello. Okay, so one of the most important differences is, right, between the string standing wave and the sound standing wave is how the particles move. So for a string standing wave, like where are the particles on the string standing wave? It's on the graph itself, right? You see, you draw this thing here, the graph shape here, that's where the particles are at. Like, if I had to go in and I had to go and color the particles, right, indicate where the particles are, right? The particles will be like here, like this here, 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 here. Like this will be where the particles are at, right? But what happens if you have sound standing waves? Like where are the particles, right? The particles are not on the graph itself. The particles are moving left and right because, like what he said, right? A sound wave is a longitudinal wave. So what happens is that the graph represents its displacement, right? The shape that you draw represents the displacement, the actual movement of the particles is based on the graph value. So if it's positive, it moves to the right. If it's negative, it moves to the left. Okay, so that was like the most one of the most commonly asked questions for sound standing waves. Like if you get a question like in MCQ, they always draw the arrows right all over the place, and it's your job to decide where is it exactly it's pointing. Right, so yeah, you have to, because sometimes they give it to you in a vertical column like that. Well, for a standing wave, the direction of travel is actually both ways, right? It's traveling this way and this way, right? Correct. So and a standing wave doesn't have direction as well. So you have to base on the graph to decide where the particles are traveling to, because you can't base it on the wave, because the wave is stationary. Okay. So there you go. Right. So just remember, that's like the key difference, one of the biggest difference between string standing waves and sound standing waves. Okay. We are now going to go into the third version. Right. Hang on. Let me just I have too many things open. Let me just close some stuff. Hang on, sorry. Yeah. Oh, okay. And then I need to close all these here. These are all like taking a lot of my. Yeah. Okay. Yeah, that's right. Okay. So, so I think I mentioned last week to you as well, right? Um, the the string standing wave, both ends closed, both ends open. Mathematically, they are the same, but then you have yet another type, which is one end open, one end closed, which is what we're going to go through today, right? Which is this picture, one end open, one end closed. Now, there are some teachers, the way they think is a little bit warped. Some teachers want students to memorize. A pipe organ is one end closed, one end open. Who's going to remember that? Nobody's going to remember that. But some teachers insist that you're supposed to know, which is absolutely untrue. There's no such thing, right? A flute is both ends open. How are we supposed to? I mean, you can know that, lah, right? I guess a flute is quite obvious. But pipe organ, one end closed, one end open. We didn't know that, right? A clarinet apparently and a trumpet is apparently different as well. So nobody's gonna, no IB question is gonna ask you that, all right? Only some teachers that are a bit up there, right? Lost a few screws, right? They think that students are supposed to know this, right? They're not, right? You're not, absolutely not. The question will tell you whether is it one end open, one end closed, or both ends closed, or both ends open. Okay, so we are gonna go with this one end open, one end closed. I'm not gonna go through all the whole the from the beginning again. I'm just gonna ask you to kind of like deduce a few things. Now it's closed end here, right? There's a standing wave now, like the first standing wave of a one end closed, one end open pipe, right? What's supposed to be at the end here? That has to be a note. It has to be a note. So we're gonna have to draw a note there. So we indicate it's a note. Okay? This is an open end. What does it have to be? It has to be an empty note, right? It has to be empty note. Okay, because it's an open end, it's a free end, it has to be empty note. What's the most basic shape of a wave that you can fit into this? One quarter, one quarter, one quarter of a wave, right? It's just a very big quarter. Okay, it's a very big quarter. So you have one quarter of like a sine wave, right? In that sense, right? One quarter, right? You can continue drawing, like something like it says one quarter. So what's the math behind this? What's the math behind this? One quarter of the wavelength of lambda one, the first harmonic, is equals to the length of the pipe. So this is the length of the pipe, right? And this is wavelength one. This is the first harmonic. First harmonic. You get this? One quarter, right? Or you can write lambda one equals to 4L. Lambda one equals to 4L. That's fine too, right? I didn't do that during Saturday's class. Then, right, then how about the next one? What's the next harmonic? Now you see, right? Remember the experiment that we're doing? I'll do it again. I'm gonna get there. I'm just trying to make you infer without the animation aid, right? So kind of like what we're trying to do is we're trying to find the next harmonic, and to find the next harmonic, we get a higher frequency, right? So we increase the frequency, right? So the wavelength will be shorter, but what will be the next shape that can fit into this boundary? Three quarters, right? It has to be a note here. It still has to be an anti note here, right? So in order for this to happen, the next possible shape is only a is only the three-quarter shape. Not nice. Hang on, let me try again. Right, three quarters. Yeah, there you go. Right. My drawing, is it complete, by the way? I need to show the dotted line, right? So I better show the dotted line. Okay. Right. Better show the dotted lines. Okay, there we go. Right. So yeah. So this one again, three quarters, right? Three quarter of a lambda is equals to L. Is that correct? Three quarters of lambda equals to L. Yeah, that's right. That's right. Okay. Okay, three quarters, huh? Okay. Here's the thing. This is where it's a bit different. Listen very closely. Oi, listen very closely. Stop taking selfies with each other. Right? Listen very closely. This is the third harmonic. Okay? There is no second. Okay? Now, in the new syllabus, IB recognizes it as first, second, third. Sorry, first, third, fifth. Right? So the next harmonic is like fifth harmonic. Okay? But in the old syllabus, right, the IB questions, like literally from IB itself, right? In the question, they ask you if the first harmonic of one end closed, one end open is like this, then they ask you what's the second harmonic. So it was very misleading at the time because when the moment they ask second harmonic, right, the idea is that the second harmonic refers to the next one. That means the third harmonic. The reason why this is third harmonic is because, right, the wavelength is three times shorter than this. Like it's in the multiples of three, right? It's in multiples of five, multiples of seven. It's odd numbers, right? So this is like, three of times one quarter of wavelength, right? So three of one quarters. And with this, right, you can already predict what's gonna happen the next one already. So what's like the fifth harmonic, right? Like how do I draw that? I have to draw five quarters, isn't it? Right? So I have to draw like five times one quarter of a wavelength. Okay, like this. So what's that? Five quarters is what? One and one quarter, right? One and one quarter. So one and one quarter, something like that. Okay, one and one quarter. So this is the antinote. Then this is the note. This is the L. Okay. Yeah. So the new IB questions should follow one third fifth. The older ones they call it second harmonic, but you realize that they asked it wrongly, right? So in a way, what they meant, right? What IB means was what's the next harmonic after the first when they say second, which happens to be a multiple of three of the first. Okay. I mean, if you had a frequency here, if your frequency is here f1, right? If this is your base frequency, right? What is the third harmonic frequency? It's three times of that frequency. Yeah, right. So f3 is basically three times of the first frequency, like this. You understand, right? Okay. Yeah. Third harmonic is, oh sorry, three times. I mean, so three. Sorry, just say lah. Sorry, I read out. I forgot to write. Okay. So f3 is three times the first frequency. Right. And this will be like five times of the first frequency. Right. There's just no two and four in the middle. Right? Because of the quarters, right? In order to fit it in, you need to draw one quarter. In order to fit this in, this is three quarters. In order to fit it in, you must be five quarters. So it ends up being first, third, and fifth harmonic. Right? I'm pretty sure that this is the new way because even ACSI also, right? The new notes I've noticed from last year's batch was that they also used one, three, and five, right? Which is the standard way. So when you get one end closed, one end open, the n value must only be in odd numbers. That means it's only 1, 3, 5, 7. If it was both ends open or both ends closed, then the n value is 1, 2, 3, 4, 5. Right? When you had this, right, both ends open, both ends closed, the n value here can be 1, 2, 3, 4, 5, right? Integer values. Okay? But when it's one end closed, one end open, the n value must be in odd numbers. So what's the general formula for one end closed, one end open? I want a general formula. So we have lambda n equals to 4L over n, right? Yeah, 4L over n. And then Fn, the harmonic, the nth harmonic frequency, it will be, no, wait, no, should be lambda 3, sorry. Sorry, one more time. This is lambda 3, this 4 times, this is, okay, this one is lambda 3, sorry. Sorry, what's the question? N over 4L. No, so I bring the 4 up, I bring the 3 down. Yeah. Right. Okay. Right. Then the Fn is, um yeah, from the last lesson, NV over 4L. Okay. So the general formula between the two different systems is just one number only. There's only one number difference, which is this one is 4, that one is 2. How do you do that? Okay, so when it's both ends open, the general formula is NV over 2L. Then when it's one end closed, one end open, then the general formula is NV over 4L. Like that's the only difference. And this equation is not in the data booklet. That's the problem. Right? So that's one big problem there. Oh, I was using my own notes over there. I had to cancel it and change it. Quite problem. But you don't need to know. You don't have to care. All right. Um, for the sake of doing this properly, let me just show you. Sorry, don't know what's wrong with me. I'm not sick. I'm just let me. I mean, yeah, just from talking a lot actually. Peaks? No. I need to reduce the amplitude. Dude, I need to reduce it down to 0. Start. Okay, so this is how one end fixed, one end open for a string wave looks like. So we just drew these, right? We just drew these. This is for the sound wave, right? One end closed, one end open. I'm showing you the string wave, one end fixed, one end loose, which is one end open. Okay? I mean, just for you to understand, if I fix it, it's a G clamp. If it's a loose end, it's allowed to oscillate up and down. I've done this before when I was doing the reflection wave thing. Okay? Other what? No end is out of the door. Yeah. Right? So I want it to reflect. Right? If it's no end, it won't reflect. It will just go, "Whee," then gone. Okay? So I want it to be a loose end. Okay, I think my question is this. What do you think the first harmonic frequency of this would be? Okay, previously in on the Saturday's class we did this. What was the frequency? What was the first harmonic frequency for both end fixed? 0.42, right? 0.42 hertz. You read hitchhikers also. Okay, never mind. Okay, so that was 0.42 hertz. Okay, so what happens when it's one end fixed, one end open? You do the math. Can we predict the math? Can we kind of like do a bit of prediction of the math? Right. So if let's say the first harmonic was 0.42, so that means 0.42 equals to NV over 2L, right? What happens when it's NV over 4L? Huh? So you're saying that 0.21, is it? 0.21. Yeah, I believe so. So which means that for the same length, if it's both ends closed, the fundamental frequency, the first harmonic frequency is 0.42. But if it's one end open, one end closed, the first harmonic frequency is actually lower. It's 0.21 hertz. Correct? So let's put that to the test. Let's use this simulation. Let's put it at 0.21 hertz. Okay, and then we see what happens. Right, and we see whether we can get a standing wave. Right, again, the amplitude is low, no damping. Damping means loss of energy. I'm assuming ideal situation here. Tension is high. This is supposed to be a fixed end. Right, one more time, this is supposed to be a fixed end. So yes, it's moving up and down slightly. It's not ideal. Right, they're trying to be realistic here. So, but it's still a fixed end. That's a completely loose end, right? It's completely free to move up and down. And I believe you get a standing wave. Right, you can see a standing wave now. So this is a standing string wave, one end fixed, one end open. So if you're doing this for your IA, like I said again, if you're doing this for your IA, if you're doing a kind of like a standing wave for your IA, yes, we can tell that there's a standing wave because there's a very large amplitude now, is at resonance, right? But how do we know exactly that it's 0.21? What if it's 0.22 or 0.23? How do we know? So in practice, what you need to do is you need to adjust. You need to adjust back and forth. So as you adjust, I guarantee you, you will see the amplitude getting less when you start moving away from the correct frequency. So then you move back again, right? You adjust it back again. So if you're doing this with your IA, please take note that you're supposed to look for the frequency that will give you the largest amplitude, which you can see now. So let's test this out by adjusting it to like 0.3 hertz, for example. Let's see 0.3 hertz. Let's adjust it. But let's start again like this. So see whether or not we can, like, like I adjust it to the right and to the left a bit and see whether or not we can get a standing wave. Right? So I think if you let it run for a while, you realize that if you're not on 0.21 hertz, which gives you the standing wave, or multiples of 0.21, you will not get a standing wave. Like it won't form a standing wave for you. What does it mean? It means that there's no resonance. It means that from the outside, right? If it's a sound wave, you can't hear a loud sound. You will hear a sound because of the original sound that's being played, but you won't hear a louder sound. Right? That's the thing here. Okay? Okay, tell me. So if 0.21 hertz was the first harmonic, what's the next one? 0.63. So we're gonna go with 0.63 and see how does it look like, right, when we create the standing wave. Okay. Yeah. At a steady state, yeah, you'll reach a maximum amplitude, right? And yeah, I guess you can tell now, right? It will reach a maximum amplitude, and that's where you know that you have reached the correct frequency. Now there'll be some margin of error for sure one, right? They'll, like, slightly, maybe 0.64 also give you very similar results, or maybe 0.62 gives you very similar results, right? But if you go too far away, like say 0.7, for example, confirm you won't get this anymore, right? So if you're doing that for your IA, right, please take note, this is how you find resonant frequency. Or if your friend is doing resonant frequency, please tell him that this is how you find resonant frequency. I have had a lot of students who join halfway through, like, doing the IAs, right? And then they tell me like, oh, they find resonant frequency by, I don't know, like when they see it oscillates, then they say that's a resonant frequency. So I ask them, you mean every other time you see it oscillate, you think that that's a resonant frequency? Then say, yeah, then the points are all random one, like completely off. Huh? iPhone slow mo. Why you be extra? Use your iPhone lah. So what happens is that you take your iPhone, right? You record the how the string is oscillating, right? And you adjust the frequency, right? Then as you adjust the frequency, you see the amplitude getting higher at some points, getting lower at some points. Then you know that you can adjust it until you get the highest amplitude. Then you end the recording lah. Don't have iPhone, no such thing lah. Okay, don't bluff me lah. Even Galaxy also can take slow mo now. See? Okay. No, but here's the thing, guys. So when you start doing your IAs, right? you realize that you can use a lot of different equipments to record whatever you need to record. Some of you might even use a microphone. You might do a string wave and you put a microphone next to it, because when the string wave is at its when it's at its harmonic, is at its resonance, your microphone will pick up the loudest sound. Right? It will have the largest amplitude, right? That will be your resonant frequency. Okay? There we go. So that's the idea, that's the basics for, right, for standing waves, right? One, two, three, right? Three different diagrams. That's all your basics here, one, two, and three. Okay? I ask you to draw this one as well, right? This is your one end close, one end open. Okay? Rest of the questions are all based on mathematics. So that means you have to go and calculate the wavelength, you have to go and calculate the speed, you have to go and calculate it. You need to sometimes they make you count also, right? They make you count, okay? Right. The next most commonly asked question for standing waves is this. They want you to compare standing wave to a traveling wave. Very, very commonly asked question. So I list out all the points for you here, right? Let's go through the points, but your job is to memorize these points. Okay? Number one, first one, look at this statement here, the first statement. What does it say? Every wave particle will have the same amplitude eventually. That's for progressive wave. But for standing wave, only the antinode particle has the maximum amplitude. Okay, some of you might be like, I don't understand this. Like, you understand this, right? Antinode got maximum amplitude. Node has zero amplitude. But you might not understand this. How come every wave particle has the same amplitude? You can say that. That's very good. Right? Let me just try one more. Let me just give you a visual for that. Let me show you this. I want the simulation. Where's the simulation? There we go. Okay. So this is your traveling wave. How do you know it's a traveling wave? It's traveling. Okay. So the wave is traveling there. Look at the particles. The particles, all the black dots. Look at how the particles, like eventually all of them have the same amplitude. Look at that. Right. So that's what my notes mean. Right. Eventually all particles will have the same amplitude. But once you create a standing wave, then the particles will behave differently. Right. So if you look at the standing wave that's being created, let me get rid of this incident and reflected wave, because let's just get to the point where you get a standing wave. So it's taking a little while because it's like traveling backwards, right? So when this happens, you will notice that, right, the particles all do not have the same amplitude anymore, right? Only some particles will have the antinode amplitude, which is the one in the middle between two nodes, and even the nodes themselves have a zero amplitude. There are some particles with some amplitudes, they are fixed, but they are not as much as the antinode. Yes, I don't have a program for that. So sorry. Yeah, that's a tough question. Yeah, but the idea is the same. Like if you imagine this to be the graph of the longitudinal particles, then there's a graph for it, right? But, yeah. I thought I showed this here on Saturday. Wait, I have to wait for the program to open it. 3, 2, 1, go. There, like that. This is a standing sound wave, standing longitudinal wave. Right? Look at this. So you see the wave, it's not traveling left or right. You see the particles, right? The particles are doing like that, like that, like that, like that, like that. You know? Yeah. So anyway, okay. Moving more points. We need to go through more points. Okay. Then what if they ask you, how about the velocity? How about the velocity? Any wave particle passing through the equilibrium will have the highest velocity, but for standing waves, only the antinodes have the highest velocity because they have the greatest displacement, so they need to travel the fastest. Okay. Progressive wave, energy is transferred from one point to another, right? Standing waves, No transfer of energy, but there's energy dissipated to the surroundings. It's still like kind of like transferred to surroundings. Okay, so it's lost to surroundings. Okay, this one is the important one. This one they love to ask many times over. Okay, this is the one you put a star on, right? Because they love to ask this question, and you got to get this right because of the frequency of how many times this question comes out. Okay, because they know. So within one wavelength, each wave particle has a different phase for a traveling wave, right? For a traveling wave. So it's kind of like if I draw this out for you very quickly, right? If you look at this wave here, let's say this wave is traveling, okay? Let's say it's a traveling wave. All the particles at this point have a different phase. That means from the first particle, let's say the phase is 0, then what's the particle at the bottom here? Like what's his phase here? Pi over 2 radians. Good. Pi over 2 radians. How about the particle here? Pi radians, right? Pi radians. How about the particle at the end there? 2 pi radians, right? So in a traveling wave, all the particles have a different phase. Starting from the first particle to this, to this, to this, to this, all the way to the back, right? They all have different phases. One complete range, 0 to 2 pi. But for standing waves, okay, you all want to copy this down first. Good. Yeah. Okay. But how about standing waves? So let's look at the visual of a standing wave again. Um, this one. This is the visual of a standing wave. Like this is the picture. Okay. Now it's gonna be hard to understand, but if you follow my train of thought, right? I guess if you just like try to understand what I'm saying, right? It should be fine. Look at all these particles here. Look at all these particles between two nodes. Notice how they are traveling at the same with the same stage of oscillation. Yes, do they have different amplitudes? They have different amplitudes, right? Do they have different speeds? Yeah, they have different speeds also, right? Okay, but somehow they tend to move together up, they tend to move together down. So technically speaking, all these particles within two nodes are in phase. They are in phase. What does being in phase mean? Okay, backtrack a bit. What is the definition of phase? Phase is defined as stage of oscillation. So if you are in phase, means that you have the same phase, means that you are oscillating together. You're moving together up and down. And every time between two nodes, two consecutive nodes, the particles are always in the same phase. So the phase difference between particles between two nodes is 0, right? Okay, I'm gonna take a screenshot here, right? Because I want to use this for a bit of my notes. So I'm gonna show you this. This is the traveling wave. I'm gonna move it to the side. I'm gonna paste the standing waves on this side here like this. Okay, and I'm gonna just color some of them. So I want you to look at these. This one here, this one here, this one here, this, and this. Right? Are they these blue ones here? Are they in phase with each other? They are. What's the phase difference Phase difference zero. So we write this down. The phi of all these particles is 0 radians. Right? That's the phase difference, right? Okay, the phi is 0 radians. How about with that that consecutive section here, like that, here? How about on this side here? Do these two sets of particles, do they have the same phase with each other? Huh? Yes, lah. Yes, they have. Because they're moving together, right? Moving together means being in phase. So these blue ones and these blue ones, they all phase difference all zero because they're all moving up together, down together, up together, and down together. But when you compare to the immediate neighboring set of particles, when I compare it to the ones here, this one's here, this, and this. What do you understand about the phase difference between these two sets of particles here? Is out of phase. It's pi radians, right? So when I compare this and this, the phase difference is pi radians, like 180 degrees, right? Technically speaking, let's not overcomplicate it. At the end of the day, the standing wave, right? Standing wave, there's only two kinds of phase difference. You're either in phase or out of phase. That's it. Nothing else really. It's not like a traveling wave. Traveling wave is this. Oh, this particle is this phase, this particle is another phase 1/4 later, this half, right? Pi radians, and then this one here is 3/4, and then this one is one full wavelength, right? For standing waves, let me just simplify it for you. You're either in phase or out of phase. That's it. That's the only two. Your phase difference is either zero or pi. That's all. How about the notes? Notes not counted, right? So when we talk about phase difference, notes are not counted. So if you're drawing this the second graph that you draw, is that a standing wave? Draw the dotted line, please. You got the dotted lines on? Yeah, draw the dotted lines. Make sure you draw the dotted lines. So if you're drawing a standing wave, again, one more time, make sure you draw the dotted lines, right? I took a screenshot here, but for your own notes, right? If you're writing this down, please make sure you draw your dotted lines like that, right? Dotted lines like this, dotted lines like that, right? So otherwise you get confused. Okay? All right, good. So let me give you a sample question, very fast one. Okay. All right. Tell me the phase difference between P and R. Between P and R is pi radians. Okay. How about the phase difference between P and Q? 0 radians. That's it. That's the kind of MCQ question you get. Right. Okay. But you see, right? I think my past experience is that if nobody showed you that thing, right? Like students will just sit there and keep wondering, right? They'll spend hours trying to figure out why is it pi radians? Why is it 0 radians? I mean, between R and Q, also pi. Yeah, between R and Q is also pi. Okay, so if you want to take this down, you take it down, right? Otherwise, right, I'll move on in just a bit. Okay, right. So that's the one of the most important things, right? They really really ask very often. Then the last row here, okay, this one is a very interesting thing to me because I haven't seen them asked yet. But I know that this is a major difference between progressive and standing waves. Like to me, right? Like this thing is like so Like, yeah, so annoying. But then yet they haven't asked it. So in order to understand the last row, right, let me show it to you. Okay, so what are we looking at here, guys? This is a traveling wave. This is a traveling longitudinal wave, right? The traveling longitudinal wave is a traveling sound wave. How do you know it's traveling? What's the clues that tells you that it's traveling? They standing wave particles are also moving, right? Okay. Okay, that's okay, that's fair. All right, sorry about that. Okay, that's fair. Any other clues that this is a traveling wave? Right. You look at the compressions. You see, this is the compression, right? This is where there's a collection of particles, right? Okay, you do you notice that the compression is traveling? Right? I mean, that's how you tell that it was a longitudinal wave. You will actually focus on the compressions. The compressions are moving. And in fact, the speed of the sound wave is denoted by the speed of the compression. Like how fast is your compression moving? You know, that's the speed of the wave. Okay. So in a traveling wave, the compression kind of like travels with the wave. Okay. Let me show you the standing wave again now. This is a standing wave. Right. Notice the compressions. The compressions don't move. In fact, the compressions are formed when the particles just happen to squish this guy in the middle, squish the node. So compressions and rarefactions are always at the nodes every half a period, right? Rarefaction, compression, rarefaction, compression. You know what I'm saying? So compression and rarefactions in a standing wave don't move, and they are focused on the node, right? The node is always the center of a compression and rarefaction. Like is that written down on my notes? Yeah, it is, right? For standing sound waves, the center of compression, right, is a standing wave, standing sound wave, right? The center of compression rarefaction is always a node. But then yet, for traveling wave, for traveling sound wave, the compression rarefaction is always passing through all the particles. Right? It's passing through all the particles. Okay? Yeah. So that's like one of the major differences that I mean I've noted, but I haven't seen them asked yet. Most of my notes are based on what they've asked before. Like kind of like collated all the, I mean, firstly, the important points, the definitions, the equations, and then I kind of like use some of the examples from some of the questions from the past, right? And then add it in. There's some rare times whereby I know that they can ask, but they've never asked it before, and I don't know why. Maybe they're just saving it for another day. I don't know. It's not gonna be a big thing. It's gonna be like 1 mark. All right. Okay. Even the A levels also they have never asked this yet. Okay. So let's move on to the next thing. Now, to do standing waves properly, I would go through the questions. However, because the main bulk of you, the next test is doesn't include C4. Okay, so I'm just gonna leave this for a later date. I'm gonna go through it, but there's no value for me to do it now. You won't find the value as well. This week we're just gonna try to clear up this C4, right? I'm gonna put C5 on pause for a while because next week, I mean this Saturday onwards, we're gonna do the practices for B5, C1, C2, C3, and A4. A4 not you lah, but got B5 no B1 You confirm only 4 chapters for you That means for the HL is a 4 plus a A4 Are you aware of what your test is on? You're not aware, now you're aware, okay? C4 is not tested. I'm just keeping up with pace. Some schools, some classes already finished C4 already. Some classes already finished C5. Doppler already finished already. Right? What am I supposed to do? Right? But for the sake of the main bulk of you, the test coming up is C1, C2, C. Okay, I may write it down, okay? All right. Your test, the upcoming test, ACSI, CT, all right? A4 for the HL A4, right? And for everyone, B5, C1, C2, C3. Okay. So technically speaking, this past week, the Saturday and today, the lesson for C4 is just to keep up the pace. All right. This Saturday, I will do the practices for these chapters. Yes, it is still double lesson. That's why I say I only hold it for 2 weeks because it's exhausting. And the 2 lessons a week, that's tough, man. Right? I get that, but I need more time, so I'm trying to create more time for you. right? So I create more time by doing that so that I have more time to do these things. I have more time to cover C4. I have more time to do practices. That's why it's double lessons. But I know it's exhausting, so I'm only holding it for 2 weeks. We'll leave the next tandem lessons for promos, right? When's promos? Next year, your head lah. You retain next year. Huh? Term 4, week 1. Oh, guarantee already shoots. Term 4, week 1 is damn early, man. Term 4, week 1. Wait. Oh, yeah, yeah. Wait. Sep House is second week, right? Sep House second week. Yeah, term 4, week 1. Physics paper is likely going to be 17 September again. This is the last. Okay. If your physics paper is on the 17th, right? 16th of September will be the last day I see you for classes for the rest of this year. I don't do things unnecessarily. I don't hold holiday lessons for nothing one, right? Only when those students start to inquire they need holiday lessons, I'll hold the holiday lessons for them. I'll invite you all to join in as well, but I'm not going to count it as lessons for you all. That's the thing. Yeah. So like yeah, correct. Yes, it is. So no, if I hold holiday lessons for those who are inquiring because they totally flunk their promos, right? Then they are the ones who will be attending those lessons. Those who are my normal regulars can just join in the lesson for free if you want. I will leave it to you, but it's going to be held in November, December, right? Yeah, see, that's why. So I don't bother to hold it then, right? Like I don't enforce lessons on you guys after the exams. So the last date I will see you for class, if let's say your exams on 17 will be like 16, and it's not even an actual class, it will be just consult only. Yeah. Then after that, bye bye. I won't see you until January next year. But I will still see you individually for your IAs. It's just no class lesson. What do you mean by IA? You better be glad that IA is compulsory. What are you talking about, man? Right? You want to do what? A level practical? 2.5 hours paper. Three experiments, two plannings. Walao eh. My first rodeo with a big batch of A level students from ACJC, like this was many years ago. They had one stupid experiment. Okay, they were given one wire, and they were given two plasticine balls, and their job was to attach the plasticine ball to the wire and make it oscillate. Right? Half the cohort spent half the practical time, right, dropping the ball from the wire. Cause you take plasticine you go and stick it in the wire then you oscillate, right? Then everything will just fall. Only the ones who are a little bit sharper, they use tape. They heck care. They just use tape. They tape the thing to the wire. Then they oscillate. They got the results, right? Then some of them go and bend the wire. They bend the little hook and they put the plasticine on and it stays hooked on and then they oscillate, right? So in their mindset, right? In the idea there was that do what you can to get some legit results, right? Okay, don't just stand there doing the same thing over and over again, getting the same falling off, splatting onto the floor results over and over again, hoping something will change. Right? It's called adaptable. Right? That's when you know who is adaptable and who's not. But here's the thing: IB doesn't require you to sit in for 2.5 hour lesson where you're so stressed about that. That was unfortunately that was a chunky 20 marks thing. So if you can't get data in the first 15 minutes, 20 minutes, that 20 marks is gone. So just be glad you guys are in IB. Okay? IB gives you all a lot of chances. Let me tell you another story, okay? I just received news from one of my ex-students. She split her exam into two. One in November, one in May. Like half in November last year and half in May. Huh? Because workload was too heavy, it was very stressful. Right? I understand. 45 points. Can you do that for the A levels? Hell no. You want to retake a paper, retake the whole damn thing. All four papers all over again. Okay, so that's why I say that when any parent asks me, do I recommend IB or IB or A levels, I always say IB. There are reasons why, right? Then they will always tell me things like, but I thought IB is only for the smart ones. Really? Because their mindset is this: only ACSI, SGI offers IB, right? Then they think that your IB is different from the international IB. It's the same. Anyway, it's still as difficult as the A levels. The technicalities is still similar. Okay, the big difference is you are given a lot of chances. right? Your IA, I have control, right? Not like the 2.5 hour practical. You can split your exam into December and May. I think you can request though. I mean that's what the ex-student of mine did. But I told her that if you don't take physics in November, I can't support you for May. Yeah, like I can only go through a few things for May only. Because oh no, that's because she was in the adjustment period, the old syllabus and new syllabus. If she had not taken the December paper last year, she would have to do the new syllabus for me. Which then but I haven't taught finish. I haven't even taught finish the syllabus by then. So I told her, please take your 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 November paper for physics and chem. Then in the end still 45 points up. I think you have the request. Yeah. I don't know. I don't know. I mean, they got 3 year IB now, right? 3 year IB. Yeah. But please do your physics in November. Okay. So these questions I'll go through after I've done that week on the practices for this to help you with your test. All right. So we just go on and try to finish up the syllabus today. Try to finish up C4 today. Yeah. I think I can finish C4. Yeah. Right? Not C5 though. C5 is Doppler's effect. I know some of you have been asking me Doppler effect questions, right? Continue to ask, right? I'll try to reply. If you see my replies in the group chat and you're like, I don't understand this, that's fine. Just wait. Okay, just give me some time. I'll come back to you. Right? There are other things that are quite important, right down here. Right? So we'll get there. Okay, free versus forced oscillations. Let's talk about free versus forced oscillations. Now, I don't know whether your teachers actually bother teaching you this. The teachers with a solid A level background will tell you the difference between free and forced, right? The ones who do purely IB from the start, they probably don't know the difference or they won't convey the difference to you. So you need to know the difference, right? There's a free oscillation and then there's a forced oscillation. What is a free oscillation? What's a free oscillation? A free oscillation, there is a one-time input of energy. Okay, free oscillation. So that means that if you take this, let's say this spring here like this, okay, let's say the spring here like this, and then you pull it down one time, okay, you pull it down one time like this. Hang on, pull it down. Sorry, what? There's one time initial source of energy. There's no further input. So a free oscillation will just oscillate, I mean, in a way, freely like that. This is a free oscillation. You understand this? Of course, in the real world, what will happen to this oscillation over time? Right? It will come to a stop, right? Okay. Why does it come to a stop? Right? Because of air resistance, right? Because of friction or whatever it is. Eventually, it will come to a stop. So for the first part, right? You know how we do physics, right? For physics, we always do this. We always understand. We always try to learn the ideal situation first. So in the ideal situation, what happens to a free oscillation? Yeah, it will just oscillate like this forever. Right. How would the graph of the oscillation of this object? You see, I'm bringing back C1. This is something to do with C1 again. You know what? So how would the graph of this oscillation look like? It's like basically a forever sine curve, right? Yeah, a forever sine curve. That means your sine curve will just go on forever. Let me just draw this for you. Say what? Yeah. Hey, no, there are some questions I haven't done for C1. The bungee jumper. Right? Yeah, that one I need to do that for the practice sessions. Right? So for a free oscillation, right? Free oscillation, right? It will basically just oscillate forever. It will just, yeah, there's no loss of energy. The amplitude will always be the same, right? And it will just continue on forever. You get what I'm saying? Okay, that's a free oscillation. If let's say it's a spring mass system, let's say it's a spring mass system, I'm gonna ask you this: can you calculate its period? A spring mass system, can you calculate the period? Spring mass system, spring mass system period. Is there a way for us to calculate it? I mean, apart from looking at the graph, but is there a way for us to calculate the period of a spring mass system? Yeah, yeah, yeah. Yeah, yeah. Good. T equals to 2 pi square root m over k. Great. Okay. So if you have the mass of your mass of your mass, if you have the mass and the spring constant, okay, you can actually predict or calculate the period of a free oscillation. You get what I'm saying? This is understood as its natural period. Okay. If you don't change the mass and you don't change the spring, right? Let's say you don't change the mass, you don't change the spring, right? Under any circumstance, let's say I extend it a little bit more, then there's a bigger oscillation, or maybe I started off with less energy, then it's a smaller oscillation. Will the period be always the same? Yes, right? Ideally, it should be the same, right? Okay, the period should always be the same because the period is only affected by m and k, right? So therefore, this is what we call the natural period of the free oscillation, which translates to, I just said it just now, the natural frequency. So natural frequency will be f equals to 1 over t. This will be the natural frequency of this free oscillation. You understand what a free oscillation is now? How to calculate the period? What do you understand about the natural period and natural frequency of a free oscillation? Yeah, right. This will be the kind of like no matter what you try to do, if your mass and k is the same, right? They will always have the same period. Like it ain't gonna change. It's just gonna be like this. Okay? Can I? Okay, good. So now we talk about what's a forced oscillation. So a free oscillation has a one-time energy input. A forced oscillation is also known as a driven oscillation. There's a continuous source of energy, right? So the oscillating system is attached to a driver or driving force that constantly inputs energy into the system. So basically something like this. So now, instead of just oscillating it like that, right, displacing one time, I'm going to continuously input energy with my hand. My hand is going to keep moving up and down like this, right? So as it keeps moving up and down, right, then the system will oscillate because there's a continuous input of energy. You understand this? Okay, so that's the forced oscillation. The one very big difference between forced and free oscillation is free oscillations, the frequency is fixed at its natural frequency, right? Forced oscillation, you can control. You can control the frequency that you want. So typically for forced oscillations, right, we have a driver and the driver has a frequency setting, right? There's a driver. I can change the frequency of my driver. So this, my hand here is the driver now, right? Is the driving force, is a driving system. Okay. So I can go slow frequency, right? My hand going slow frequency, right? Or I can go higher frequency, right? So I can go higher frequency. So based on what I want my hand's frequency to be, right? The oscillating system will follow the driving frequency. So if your driving frequency, so you see, the forced oscillating system will oscillate at the driving frequency. So if your driving frequency is high, then it will oscillate at a high frequency. Then it's 0, 0, 0, 0, right? So the forced oscillation follows the driving frequency. So one more time, I reiterate this. Free oscillations, only natural frequency. Forced oscillations, right, at the driving frequency. And you can change the driving frequency. You can adjust. You want your driving frequency to be high, you want it to be low, no problem, can. Right? So again, free oscillation is a one-time energy input, one time. Forced oscillation is same oscillator, but now you have a driver on top, and the driving is like, the driver adds energy into the system continuously. Okay, good. Yeah, and this next part is super important. Free oscillations do not experience resonance because there's no driver. Free oscillations, it doesn't make sense for about resonance. Yeah, the amplitude is whatever you start off with. right? There is no driver. There's no input of energy. It's not like a flute. A flute, when you blow air into it, it makes the sound. You're inputting energy. Like you blowing into a flute is the driver. You know what I'm saying? Okay. So free oscillations, resonance doesn't make any sense. But for forced oscillating systems, you can reach resonance if, I think some of you might have heard this in school, but I'm just going to say it first before I show you how you understand it, right? If the driving frequency matches the natural frequency of my oscillating system. So there are two kinds of frequencies here. Number one is the natural frequency of my free oscillator. Two is my driving frequency, which I can adjust. If I adjust my driving frequency to match the natural frequency of my system, I will get resonance. What is resonance again?
It's when the frequency of the natural oscillation matches the internal.
No, okay, that's you talking about the conditions to reach resonance. But what is resonance? When what? It's like a standing wave. Okay, so we moved on from standing waves. So this no longer, I mean, it is still similar, but right now I'm bringing back C1, so it's about the oscillator again, right? So, but essentially, whether is it standing waves or is it this one here, what's a key feature of resonance? The amplitude becomes larger. You get a larger amplitude. So resonance means you get the largest amplitude possible. Resonance is when you get the largest amplitude possible. Okay? So down here, you see, resonance is maximum amplitude. Okay, resonance is maximum amplitude. So I'm gonna try to demo that in class. I'm not too sure whether I'll be successful in doing this, right? So I'm gonna try to demonstrate this. So I don't know exactly what's the frequency of this thing here. So I'm just gonna adjust my hands movement to see whether or not I can get a resonance out of this spring here. So I'll start off with a slow frequency like this, right? Like that. Okay. I mean, it's supposed to be fixed up, but I have to move it up and down a little bit, right, to give it energy. So like that. Okay. So the system, is it oscillating with my hand the same frequency? It is, right? Do you think it looks like it's resonating? I don't think it looks very resonating now. Okay. Okay. So what I'm gonna do is now gonna change the frequency of my hand. Okay. And I'm gonna try to match it. Basically, I can change it until I am getting something like that. Right? So obviously you can tell that there is resonance here, right? The amplitude is going haywire, right? Okay, that's because my hand here, I intentionally change the frequency so that it matches, so that I can get my spring to do this. What if I continue to increase the frequency? What if I do very high frequency on my hand? Okay, see what happens when I do high frequency, okay?
Then there will no resonance cause.
Look at that. So my hand is vibrating at a high frequency, but what's happening to the amplitude of the system?
No.
Nothing, right? There's no amplitude. So it's not like the higher frequency you go, the more amplitude you get, it must match it must match to the natural frequency. So at some certain frequency of my hand, I don't know how much is that, my spring is doing this mad, like amplitude bouncing thing. So force oscillations, the driving frequency must match the natural frequency. Too low, no resonance. Too high, also no resonance. Okay, there you go. We'll talk about the energy thing later, but that's what I was trying to demo to you guys, right? That the frequency must match. So you have the driving frequency, so I'll call that FD, and I'll call this F naught. So usually the driving frequency is, I mean, they just put it as F, I put FD for example, but F naught is the natural frequency of the system. Okay, and they must match. So if FD equals to F naught, then you get resonance. Can I? Okay, so resonance only applies to forced oscillations. For now, let's go back to free oscillations. Let's go back to free oscillations and let's talk about how damping affects free oscillations. right? How damping affects free oscillations. Okay, so down here, this page here. Okay, right, we're on this page now. This is how damping affects free oscillations. Free up, right? This is free oscillations, okay? Right, we'll come back to forced oscillations later, but for now, let's do free oscillations. Okay, firstly, how do you damp this oscillation?
Order to constantly
I mean, yeah lah, right? I mean, how do you damp this oscillation? Like damping.
use errors.
So there's air, right? So the idea here is this: in the real world, when you have an oscillation, eventually this oscillation will slow down. Eventually, it will return to equilibrium because there's no more energy, right? All the energy has been dissipated to resistive forces, right? Yeah, this will be considered, if it's just air resistance, is considered as light damping. Okay, light damping. How else can I change the damping? Okay, one common mistake that students make thinking about changing the damping is add more mass. Adding mass does not change the damping. Adding mass changes the period. So you cannot say I add more mass, then I can increase damping. That's wrong. But how else can I increase damping, guys? Anyone? I can put a piece of paper in the middle like this. You may do this for IA as well. Put a piece of paper like this, and then the piece of paper will add on to the air resistance, right? So as it oscillates, it will have more air resistance. You can use an even bigger piece of paper if you want. Then you add on even more air resistance, right? Then you can do this IA called coefficient of damping. Yeah, coefficient. Now, it used to be a popular topic that I suggest for students to do because this was not in syllabus previously. Like this is a new topic to the new IB syllabus, right? So damping is a new thing. Okay, yeah. But the reason why I mean I know what's going on here is because the A level students do this like for the last 40 years already. Okay, what else can you do to increase damping in this system? You can put it in water. You submerge it in the water, right? Then you basically increase the fluid resistance to become water. So as it's oscillating, it's going to oscillate in water, right? Or you can even oscillate it in oil. That will increase the damping, correct? For the most part, we consider all these kind of cases as light damping. Okay, so if there's an undamped free oscillation, how would the graph look like? This will be like xt, right? Xt. The undamped oscillation will look like this. Okay, I'm just gonna copy and paste it. This is undamped. In fact, I'm also gonna use a different color for this because otherwise it might be a bit misleading. It get a bit confusing also. Let me change the color of my this thing here. This is undamped. I want to change the color to maybe a bit gray. Yeah, like this. Okay, so I've just drawn a gray line here. This one here. This is undamped oscillation. No loss of energy. No decrease in amplitude. Right. I was talking about the joke the other day. Right. I don't know whether you caught the joke. Right. Damping. Please remember it as decrease in amplitude. That's why it's called damp. Right. Decrease in amplitude. Damp. Damping is not making something wet. That's called dampening. Right. So damping means you decrease the amplitude. Okay. And so this is an undamped example. This is undamped. Undamped. Please do not misquote this as underdamped. This is not underdamped. This is undamped. Okay, so there's no damping, right? So it will continue oscillating like this forevermore. All right. What happens if you have? What happens if you have? Um. Okay, so for free oscillations, there's only three types of damping that you want to consider: light, critical, and heavy. Let's draw light damping. So light damping will look like this. You sort of like still follow the same curve, but with every turn, you decrease the amplitude. You decrease the amplitude, but you follow the same period. You follow the same period. So light damping is when there's a gradual loss of energy, right? When there's a gradual loss of energy, right? There's a gradual loss of energy, but the period is still the same. So light damping, right? Loss, gradual loss of energy, right? Same period. Can? Right, so yeah, yeah, take some time to draw it. If you have to draw it, take some time to draw it. The thing is that I suspect at some point they may ask you to sketch. So I am pretty sure that that you know the at least for the past 1 year, right? I have not seen any teacher make the students draw this yet. But this is a very common thing that they like to ask. I mean, at least from the A level side, lah, right? So there was no past year questions on this, right? Because this is a completely new thing that they included. For for me, what the cues I'm taking from the syllabus and from the textbook, right? So I was following the so-called textbook, and they listed all these down. So I'm like, okay, I think I better just bring it up. There's a lot more complexity to this, but I'm just gonna keep it like as simple as I can. It's just like tedious because you have to draw the graph. Okay, now critical damping. Let's talk about critical damping. Critical damping is a special type of damping. That means that the amount of damping exerted on a system is so much that it returns to equilibrium in the shortest possible time without performing any oscillations. This is what we call critical damping. So for critical damping, usually we start off from here, right? We start off from amplitude and then it just goes back down like this. This is an example of critical damping. Okay. So critical damping is like I try to oscillate it, I bring it up to an amplitude, I let go of it, it whoop, come back to origin. Like it didn't even manage to oscillate at all. So it's the shortest time possible without performing oscillations. This is critical damping. So I mean, what's your job? Your job is just to recognize the graph. If let's say they show you this graph like this, then they ask you, okay, what type of damping is this? Your job is just to call it critical damping. Like there's nothing else, right? They're not gonna ask you, oh, why is it like that? Right? So if they ask you like this, like why is it like that, you can just say that the amount of resistive forces are so strong that it actually brings it back to its original, right, position. I'll give you an example. It's a rough example. It's not an exact example because if I give you examples, chances are some of you might even misquote or mishear this and then start thinking about all the weird things. All right, I'll just give you as an example. It's just the best I can do, right? So I want you to think about it as like a swinging door, right? Imagine a door that can swing because let's say the hinges is let's say the hinges swings both ways, right? There's no ledge to kind of like block it, and therefore the door can swing backwards like this, right? So let's say you open the door and you let go, then the door will just kind of like sweep like this, right? Okay. Eventually the door will close, right? That will be the what? That will be the light damping. For critical damping, let's say you imagine a door that's undergoing critical damping, right? For critical damping, the spring, the restoring spring, is so strong, it pulls the door, slam, and then there's a latch and closes it, slam shut. Like then the whole system there is called a critically damped door. A critically damped door has something to pull it back very quickly and something to prevent it from oscillating, right? Then it just slam shut. I'm quite sure you have experience with that kind of doors before, right? Open, let go, come. Is it your house main door? Not your house main door. Like there was once my contractor, he go and fiddle with the spring and then he left it in a very bad configuration. So every time we open the door, we let go, right? The thing will just close like that. So that was a critically damped door. Okay, that's all you need to care. There's no math, there's no physics. I mean, there's no math based physics. There's no math to this thing. There's no equations, nothing. That you just have to kind of like visualize what is a critically damped door. That's it, right? And the reason why it's doing that is because the spring is so strong. Bam, right? It gets pulled back very quickly, and then there's a catch, right? It catches the door, so it slams there like this. So what we need to do now is we need to go and see how does a over heavy damp door look like. Now the wording is a bit weird because when I was doing this myself, right, in my own days, right, many years ago, we used to call it over damping. I don't know where it changed, and it changed to heavy damping for the A level side and for the IB side also. So I was like, I've always thought it was called over damp, but no, it's called heavy damp. That's why when I was first teaching this last year, I kept saying over damp, over damp, over damp. Then all of them looking at me like, but your note says heavy damp. Then I was like, yeah, my note says heavy damp because I just kind of like look at the textbook and I copy the words that they use, right? But then my mouth kept saying over damping. So just take note, if you see any homework, some teachers may use very old questions from last time because there is no IB questions for this, right? So they may use very old questions, and old questions uses the word over damping. Okay, so we're gonna draw the heavy damping one now, right? So we're talking about heavy damping. Heavy damping is basically the system returns to equilibrium after a very long time, but also no oscillation. So how does that look like? So overly damped systems will look like this. You open the door and then it takes forever to close.
Is it like
Shopping mall doors. Yeah. Right, so it goes like that. Like this. Okay? Right, so this is an over damped, heavy damped door. Heavily damped, right? Heavy damping, sorry. Heavy damping. I just call it heavy damping. Woo! Okay, any questions on this? Are we on force oscillations here? Is this anything to do with force oscillations? No, right? It's pre-oscillations, right? Okay, guys, take a quick break. I need to settle something outside. Hang on, I'll be back. Pass the snack around, please. Pass the snack around. I think there's no thing to do.
no? No. Your test tomorrow, right? Maybe. Huh? Mine's on the. Okay, oh yeah, that's it. What's yours? Good deal. Very fast. Okay, then you all take a break anyway. Because your brains are gonna be fried already. So my brother bought a drone for me, DJI. Then unfortunately I felt that it was a bit dangerous for the kids. So I wanted to exchange for the one with the blade guards. Yeah, Loy Xingjian, your Chinese teacher in ACSI, the photographer. No, you don't know Loy Xingjian, Mr. Loy? No man, ACSI, your Chinese teacher, Mr. Loy. Yeah, Loy lah, yeah, yeah. Yeah. So anyway, yeah lah. No, 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 no. Leong, not Loy, not Loy. So I had to return it. So the DHL had to come and pick it up. But this thing is damn costly, man. Um. Oh, forgot to label this. So this is light damping, right? It's light damping. Huh? The two of you fight lah. Yeah. I cannot already. Hey, can you pass the snacks over? There's like chocolates and there's Hanuta there also. Come on, man. There's Hanuta. Yeah, yeah. Pass it down, man. Pass it down. Yeah. Anyone wants this? This is like massive, right? Look at that. It's crazy. Just help me keep it neat first. Now here. Yeah. So what's up? Ah, what? Is she old? If she really? Uh, what's her surname? I know a Lydia Ho. Lydia Ho? But she retired already, right? Lydia Ho? I don't know. So there was a chem teacher called Lydia Ho last time. She was the reason why I topped the level in chemistry. Yeah, yeah, last time. Yeah, stupid me, right? I chose chemical engineering thinking that it's something to do with chemistry, right? Yeah, dumbass me. It's all engineering. It's all math. Oh my god. Ugh, I suffered, man. If you take F math, then you go into engineering. It's actually very easy. If you take further math and you go into engineering, it becomes very easy because a lot of the math that you do at this high school, right, when you go on to university is reapplied again, then it becomes very easy. But then no, I didn't realize it was all. I didn't realize it was all like math and all that. So oh god, I hated my 4 years there. Oh yeah, sorry, sorry. Yeah, I think I mentioned to her also that I don't like chemical engineering. Like it was just a means to an end, cause like they have money at the time, so just do whatever I can, right? Anyway, I mean I hated it so much that after I graduated, I just went to work for a bank, right? So yeah, I was a banker for 7 years. Yeah. Huh? When did I start teaching? You want to guess my age? Is it? No lah. I can tell you, no worries. I started in 2015. 2015. Holy crap! Yeah, yes, yeah. Now that I think about it, yeah, you're right. 2015. Hey, excuse you. Yeah, 2015 lah. So 10 years lah. 10 years. The first batch of the students, yeah, some of them doctors now already. Like they've been practicing for the last 5 years already. Yeah, some of them are almost gonna finish their consultant exams as well. Yeah, met up with some of them recently also. No, that one is the center here. That one is just a joint uh, decision between all the other tutors here who are sharing the rent to decide to label the signboard. It's not an official thing. Yeah. The official name is this one lah. Yeah. Pass the stickers around lah. Yeah, that's the official one. Yeah. That's all. Yeah. No, unfortunately, the sticker doesn't really work on a black background, so you have to paste it on a white background. Then so you can see. You paste it on a black background, you can't see anything. Yeah. Straightforward. Depends on what you want to do. Do you want to do chem or math, right? Yeah. The one is chemistry. Yeah. She usually takes on the, how do I put it? How do I put it in a politically correct way? She usually takes on the more difficult cases. Ah, right. And then so chemistry, right? I mean, secondary school chemistry. What's the most important thing for secondary school chemistry? Solubility table. Yeah, solubility table, chem bonding, and preparation of salts. No, here's the thing. Like none of your chem matters if you don't get those three things correct. Chem bonding, solubility table, and preparation of salts. You can't get any of those right. You can forget about the rest of your chem. No, that's the thing, right? So most people who miss out the first 4 months of chemistry, they will suffer for the rest of chemistry. Like they don't understand what's going on also because of the first 3 months, because of the first three topics. Yeah. No, legit. I mean, more concept also. Okay, a lot of people think that, oh, I'm not good at more concept. No, you're not good. You're not that you're not good at more concept. You're not good at chem bonding because you can't figure out the formula for nuts, and that's why you keep getting the ratios wrong because you got the chem formula wrong. Yeah. I mean, I used to teach triple science, right? So I know the common pitfalls for students who do chemistry. Like I know why she's screaming at them, right? I know why. That's why I stopped teaching chemistry, you know. Yeah, because I ain't got any energy to go and scream at people anymore already. It's like if you don't want to memorize your solubility table, it's none of my business. I'll stop teaching altogether. Yeah, yeah. I used to teach triple science. Like since 2015, but I only specialized in physics only around 2020, about 5 years ago. Then I only, yeah. But even no, I've been teaching triple science since 2007. Yeah, 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 yeah. When I officially, when I was working as a banker, I was still teaching on weekends. Yeah, you just do it, oh. Yes, chiong ah. Yeah. You see the HDB prices or not? No choice, right? I was in Barclays, then I was in Citibank for risk management, and then I ended up as UOB. But UOB, I was doing relationship manager, so I was handling clients and all that. Yeah, yeah. I mean, UOB was where I made my most money. Yeah, even though it's a local bank, but that's where I made my most money. So even my first job, investment banking, I didn't earn as much as I did in my UOB job. Yeah, UOB job, I mean, I got 14 months of bonus for 1 year. Yeah, yeah. That's when you chiong lah. That's when you chiong lah. So during my UOB years, I stopped teaching for 2 years. Then after I earn the money already, I can buy house already. Okay, heck it, I just quit. Okay, okay, go. So I just showed you the demonstration of force oscillations. I already showed it to you. Okay, so force oscillations means that there is a driver, there's a driving force, and then your oscillating system at the bottom. So this is your oscillating system. So the first question is okay, like what are the three ways to determine the natural frequency of an oscillating system? And I think I went through that just now. First one is to calculate it. Let's say it's a spring mass system. How do you what's the you know what's yeah what's this thing here, right? So your t equals to 2 pi, right, square root of m over k. Correct? That's one way. Another way is really go and set it in motion and then do the video recording and then record a period lah. That's it, right? Record 20 times, take the time, divide by 20, that's one period lah. Okay? Or number two, apply a driving frequency that's adjustable and test which driving frequency will cause the system to resonate. So here's the like the reverse trick. If you don't know what's the natural frequency of this system, right? Maybe because the driver is always stuck to it and the driver is always running. So the one way is that you can adjust the driver's frequency until you see the system resonating. Then whatever the driving frequency is, it will definitely be the natural frequency of the system because that's what resonance is, right? That's what resonance is all about. Okay, one more time. I repeat it again, right? So the third way of finding the natural frequency of a system, right, is to adjust the driving frequency, right? Adjust, right? Test which driving frequency, right? Test which driving frequency, right, will cause this system to resonate. Okay, and that will be the natural frequency of the system. Driving frequency will be equals to the natural frequency of the system. Ah, the second one is just basically what you were doing back in secondary school. 20 oscillations, record the time, divide by 20. Like literally, you just record it, like physically the period. Then once you record the period already, you can use the period to go and find the frequency, right? That's just the most direct method, right? But there are three different ways of finding the natural frequency of the system. Okay, let's go on to the next page. Sorry, these pages are like very big and blank. Don't know why also. So now we do force oscillations with damping. Force oscillations with damping. Okay, so force oscillations and free oscillations are two different things, right? Force oscillations and free oscillations are two different things. So what happens when you try to damp a force oscillation. So I think one of the key things is again to remember force oscillation means what? Means that there's a continuous input of energy, right? There's a continuous input of energy. So let's say I'm like, this is the force oscillation, right? What happens if I try to damp it? Kind of like just now, right? I use a piece of paper, I add it in, I slot it in, I increase the air resistance, right? Okay. Wait, hang on. So I oscillate with a piece of paper, so the amplitude will be less, right? Okay. But I think one of the key things is I want you to remember this, does a force oscillation ever go back to rest? Does it stop? It never goes back to equilibrium, right? So that's the thing. Why? Because there's a continuous source of energy. Like the energy is always being input. So whether or not the amplitude is very small or not, it is still oscillating forever. So there's no such concept of force oscillation going back down to equilibrium. You know? So the idea here is this is the amplitude. Huh? I mean, if you set the driving frequency as zero, then the amplitude is zero. Okay, so usually, right, for this graph, I don't like to start from zero. Like it would hardly make any sense. I will start from somewhere around here like this. Yeah, I'll start from there. I will start drawing from there. Okay, but what I'm trying to show you here is, right, we are changing two things. So first, we are changing the damping. Two, we are changing the driving frequency. So we are changing both things, right? So if there are two moving targets, you should only always change one by one. So let's do undamped first. No damping. Okay, no damping, force oscillation, undamped force oscillation, increase driving frequency from a setting of low to high. Okay, how does the graph look like? The graph will look like this. Like that. The idea is to show that the graph can go all the way up there, out of the range of the graph, right? It's basically a sharp point at the end, right? Yeah, right. So resonance happens somewhere at the peak there, right? Because resonance is the maximum amplitude possible. So when you draw it back down, this will be F naught of an undamped system. Bless you. Okay, so this would be like the natural frequency of an undamped system. Okay, then what happens when you introduce some damping? So let's say you introduce some damping. That means you put a piece of paper, right? You put an extra piece of paper here like this, and you increase the air resistance that it experiences, right? So and you try to do the whole you try to to change the driving frequency from low to high again with a little bit more damping. You get what I'm saying? Okay. So then the new graph will look like this. Oops. Wait, sorry. It's like that. It's lower, yes. It's a peak like this. Okay. So sorry what? So the natural frequency will also shift to the left, right? And maybe I'll call this F1, right? Not F0. So F1 will be the natural frequency of a slightly damped system. And what happens to the graph if you keep on increasing the damping? What happens to the graph if you keep increasing the damping? So if you keep increasing the damping, the graph will go like that. Right? You just need to draw three, right? That's all. Okay, so this is undamped, right? This is an example of undamped or very light damping, very little damping. This will be like slightly more damping, slightly more, and more,
Okay, there is no specific words for the damping for force oscillation. So we don't say like critical damping or heavy damping or light damping. We don't say that. So basically for force oscillations, the graph here, right? Basically you just see that, right? Undamped, then go for more damping, then even more damping, right? What's more important is what happens to the characteristic of the graph. So what do you notice? Like what you're saying? What's the first thing you notice? Basically, with more damping, amplitude throughout the entire thing will be less. More damping, less amplitude. Okay, less amplitude. Again, one more time. Is this does it mean that it returns back to equilibrium? No, right? It's always oscillating, right? It's always oscillating. It just has less amplitude, right? When you have more damping. Number two, what's the other thing you notice? Right, the resonant frequency, the resonant frequency or the natural frequency, right? So resonant or basically the natural frequency decreases, means it shifts to the right. I mean left, sorry, shifts to the left. Okay. Number three, the peak becomes broader. It's a thing, right? The peak becomes broader. Okay. This is you finally, I think, making sure that you know that there's a difference between the graph of free oscillations with damping and the graph of force oscillations with damping. For force oscillations, there's an indication of resonance, right? There's the peak here, there's the resonance, there's resonant frequency, right? Force oscillations never goes back down to zero, so even at high frequency, right, it doesn't touch the zero graph here like this. Okay, like the amplitude is like some crazy value when you match the same frequency. And then for free oscillations, there's those names, right? There's the names of like what critical lah, heavy lah, undamped and light damping, right? All that, right? For force oscillations, don't have force oscillations. And I hope you understand that these two graphs are actually not related to one another because they're two different systems, right? This one is a continuous source of energy input into the system, right? The other graph has this is a one-time energy and therefore it dies off after a while, right? Sorry? Yeah, yeah. We won't let it touch you. Okay. I think maybe just one last question here. This one here. So we understand resonance, right? Again, what happens at resonance? Okay, what's the condition for resonance to happen? The driving frequency must match the natural frequency. Then what do you get? What, sorry? Yeah. So what happens during resonance? The amplitude becomes maximum, right? Maximum amplitude. Correct? Right? So that's what resonance is, right? But how about the energy? How about the energy? Okay. So if I have a oscillating system, right? This is my driver, okay, and my oscillating system is like this. If let's say my driving frequency matches the natural frequency of the system, okay, in terms of energy, energy is being transferred from the driver to the oscillating system, right? So energy is being transferred from, so the energy of the driver is being transferred into energy of the system, correct? At resonance, basically what you're getting is the maximum transfer, the maximum efficiency of transfer. So at resonance, right? So this is at resonance. At resonance, you are getting the maximum rate of transfer of energy, right? You're getting the maximum rate of transfer of energy. right? So whatever energy that your driver can provide is being transferred to the system. That's why the system's amplitude goes haywire, right? It goes super high, right? So that's the whole idea, right? So right, then you have your max amplitude and your max amplitude, right? Like this. Okay, so this is what happens when it's at resonance. But I also want you to understand that energy cannot be stuck somewhere, right? Like let's say for example the driver is a mechanical driver, like a motor, right? Electrical energy goes in, KE of the motor. Motor makes the object move up and down. There's very big KE, there's very big GPE, right? But at some point, the amplitude reaches a maximum. Like it doesn't increase infinitely, right? Amplitude, right, does not increase infinitely. So it's at a maximum, but does not increase infinitely. Infinitely does not increase infinitely or infinitely, sorry, right? Yeah, doesn't keep increasing. You see, would you expect it to increase infinitely? Would you not expect it to increase infinitely? I keep on adding in energy. Energy is being transferred to the system. This system gets more and more and more and more and more energy, right? The amplitude should increase higher and higher and higher and higher and higher. But we know that most of our systems, right, we actually get a maximum amplitude. It doesn't go any higher than a certain point, right? So it doesn't increase infinitely, right? So what's happening to the energy? Like, after the energy has been transferred enough for it to oscillate already, then what happened to all the surplus energy? So just take note, in real life situations, in real situations, there's always still dissipation of energy to the surroundings. So it doesn't increase infinitely because, right, any surplus energy, right, surplus energy is dissipated to surroundings. Okay, dissipated to surroundings. Can let me kind of like show you this. So again, one more time, like this example here. So if I match the natural frequency of this spring's amplitude will go haywire like this. This is me having a very efficient transfer of energy from my hand to the system. You see that? Okay. But what if my frequency of the driver is doing this? Right? I'm actually putting in a lot of energy, my system here is has a very high frequency, correct? So I'm actually transmitting a lot of energy. I'm using a lot of energy. I'm inputting a lot of energy, but the energy is not being translated to the amplitude of the system. So where is this energy going? The energy is being dissipated out to surroundings, right? Okay. The idea here is this: at resonance, right, you have the most efficient transfer to the system, right? If you're not at resonance, you're basically wasting energy to everywhere else. Okay. So at resonance, you get the maximum transfer. You do get the maximum transfer to the system, transfer of energy to the system, right? But your amplitude doesn't increase infinitely because there's some energy that's being dissipated to the surroundings. But if you're not at resonance, you're basically sending out a lot of energy to the surroundings. So maybe I illustrate this for you. All right, let me just draw it out for you. So this picture here, I was trying to show you at resonance. But what happens if I did that thing, right? I was like vibrating this very very quickly, and then the spring at the bottom was just kind of like not really oscillating by much. Okay, so the idea here is when it's not at resonance, there's a lot of energy being dissipated out to the surroundings. A lot of energy wasted to the surroundings. Okay, but it's a one for one. It must be transferred completely out, right? So for resonance, let's say you have 100 joules, 80 joules is given to the system, 20 joules is given off to the surroundings. If you're not at resonance, maybe an example is 100 joules goes into the driver, right? 20 joules goes to the system, but 80 joules is lost to the surroundings, right? Just just to give you some numbers to help you understand.
Yeah, so and let me just put this in first. 100 joules. Wait, hang on. Then at resonance, right? Since it's at resonance, like 80 joules is given to the system. Oh, oops. Right, 80 joules given to the system. Then dissipated 20 joules to surroundings. But when if you're not at resonance, you could have 100 joules here, 20 joules given to the system, and 80 joules wasted to the surroundings. So even if you're yeah. Not at 20 joules, then it could be only 40 joules given to the system. Huh? What? Sorry? If it's 120 joules. Oh, if it's 100, I mean, it might be by proportion. I don't know. I'm just giving you some numbers to give you an idea. Is that why the amplitude is more? I mean, the amplitude is less because there's more energy wasted to the surroundings. So when your driver matches the natural frequency, you transfer most of the energy to the system, right? So 100 joules goes to this guy, 80 joules, right? And the 80 joules is used to oscillate the system, right? But then as you continue to supply energy in, like, you keep losing energy, but there's a maximum efficiency of transfer here, okay? Whereas for this one here, this one 100 joules goes from the system into the oscillator, right? Sorry, the oscillating system, right? But because it's not matching the frequency of this guy, so you're actually wasting a lot of energy to the surroundings. Like my hand is moving up and down very quickly. I'm just working against the air resistance, right? Okay, and only 20 joules is given to the system. Like this, just this arbitrary numbers. I'm just showing you the numbers, like just give you an idea on it. It's not even like 100% accurate. Okay, but I'm just showing you that when you're not at resonance, you're wasting more energy to the surroundings. But when you're at resonance, you're supplying more energy to the oscillating system. That's why the amplitude is very high. Yeah. Okay. Now, yes, I'm done here for today. We're at the end, right? That was the last slide, right? Yeah. These are the sample questions which I'll do next time. Okay. For for the next lesson for you guys, right? Because this is like the second lesson of the 4 lessons, right? Of the double lessons for 2 weeks. For the next lesson, we are going to do some questions, right? We're going to start doing some questions. What? So we're going to start with C1 first, right? We're going to start with C1. In my notes, there was a C1 question which I skipped, which I said I will leave it later for the term test, for the CT. So if you look at the C1 notes again, if you go back to the C1, does everyone have the C1 notes here? Okay, right. I had these notes about a bungee jumper. Do you remember seeing that somewhere? Was there a bungee jumper? Yeah, this one here. Okay, we're gonna. Oh, there's no question. There's just information only. There's only information here. Okay lah. I guess I'll do that this Saturday. Because if I say that do as homework, I think I also don't know any of you will do homework or not. But we'll start with this, and then we'll start with the other question I sent in the group chat. I think the other day someone asked me this question. This question here. This was the IB question. Yeah, this one here. This was the IB question. Very misleading. What do you call it B2? It's not B2, man. This is C1, right? This is your school worksheet. Yeah. So the example I have in my notes is very similar to this. But I'll do my one first, right? Then you can try to do this one as well. Okay. I didn't want to, not that I'm gatekeeping lah, my gosh. Alright. It's just that I specifically did not go through this example when I was teaching C1. I said that we're going to do this for the test, right? To prepare you for the test, because maybe it's closer, maybe you remember it better, right? So I'll do these 2 questions, right? Starting this Saturday. So this Saturday, one class only, I'm going to do C1 questions, try to mix in with a few C2 and C3. Next weekday, that means next Monday and Wednesday, I will do B5 mixed in with A4. Because your test also got B5, right? Yeah, your test, you know what B5 is? Circuits, potentiometer, right? That's like the biggest thing that they like to test for B5, right? Every year IB has this potentiometer question, every year. Okay, so if you have no idea what a potentiometer is, right? Those who want to, I mean, you want to refresh, you drop me a message for the B5, right? Because I went through B5 very quickly. Right. I remember doing it very, very quickly. Then there's A4 also, right? A4 practices. We did some questions for A4. I think I did a lot of examples in my notes for A4. So, that's why I'm not too worried, right? But for C1, C2, C3, I'm worried about the practices. Can? I know lah, it's a CT, right? Some classes will get the paper first, some classes will get it later, right? Okay, that's not the point. The point is, I'm only going to see you up to 16th of September. After that, I'm not seeing you already. So I don't want you to come back. Right? That's it. 16th September, get your grades, get your 7. Okay? 2026 January, see you again. Okay, those online, thanks very much. See you guys. Bye bye.